The last thing we talked about was how if part of the region that is inside the interval from a to b goes below the x-axis, then the integral will take the area above and it will subtract the area below. Okay, so in this example where we had a 4 up here and this region down here has an area of 9, the total area is actually 13, but if we evaluate the integral, we get the area above, which is 4, and the integral subtracts the area below, which is 9, and so we would have a -5. Okay. Also keep in mind the definition as we talk about these next properties of integrals. We're going to go back to that a decent amount just to make sure that that makes sense. Okay. All right. So first property here is that the integral from a to a, from any number to itself, is going to be equal to 0. So if I'm integrating some function from here to itself, there is no delta x, there's no horizontal change. So delta x is 0 every time, meaning in the definition, we would have f of x times 0 plus f of x times 0. Like we don't have any width. So if we integrate from something to itself, we get 0. Okay. Next, if b is between a and c, then the integral from a to c can be split as the integral from a to b plus the integral from b to c. So visually, let's say we have, I'll just use a positive curve. So if I have a and then b and then c, the integral from a to c, because this function is positive, would find all of this area. Well, if I do the integral from a to b, that would give me this area, plus the integral from b to c, which would give me this area. So I have a total of the same amount of area as integrating from a to c, okay? So for example, if I am given the integral from the value of an integral from 1 to 5, and also the integral from 5 to 8, I can find the integral from 1 to 8 by adding those two together, okay? The next property says if c is less than d, move this for a second, I can't get to my, there we go. Sorry, I'm trying to move things around on the screen. Okay, if c is less than d, in other words, c is to the left of d, the integral from d to c is the opposite of the integral from c to d. So when we write an integral, we write our limits as the lower value and then the higher value, okay? If we're given an integral that is backwards, then what we need to do is we need to flip those upside down and then put a negative out front. So let's talk about why this happens. So here's a function from c to d, okay? If we integrate from d to c, then according to our definition, which remember comes from that infinite Riemann sum, this right here is x sub 0, this right here is x sub n. So when I'm finding delta xi, okay, I'm going to be doing a smaller number. So x sub I would be smaller than x sub I minus 1. I got that from what we talked about right here. Okay, where delta xi is the difference between x sub I and x sub I minus 1. So in other words, delta x3 was x sub 3 minus x sub 2. The change in x for the fifth rectangle, for example, delta x5 would be x sub 5 minus x sub 4. Well, if I'm starting with x sub 0 on the right and I'm moving this direction, then let's say that this is x sub 4, x sub 3 is a bigger number than that because it's further to the right. And so now I have a number minus a bigger number gives me something negative. So my delta x is going to be less than 0 if I'm going from right to left. So the way that we switch this is we flip it upside down, go from C to D, but then we put a negative in front because it will be the opposite of what we would get if we go from C to D, okay? So if your bigger number is on the bottom, flip them and put a negative in front. Okay, and then the last property here is that x is a dummy variable, meaning it does not matter what letter is inside here, okay, as long as the integrand and the differential are written in terms of the same one. The output of a definite integral is going to be something numeric. We're going to have some value. Like up here, the output was -5. The output of an indefinite integral gives us, remember that's where we don't have the limit, so something like just this. is an antiderivative function. Okay, the output of an indefinite integral is a function. But if we have a definite integral, the output is going to be some numeric value, okay? Because it's going to be some numeric value, it doesn't matter what letter we have on the inside, okay? Whether it's f of x dx or f of t dt or whatever, the output is numeric. So we call that letter or the variable on the inside a dummy variable, and it doesn't matter, okay? All right, so let's do a couple examples. We will be tying the idea of definite integrals to antiderivatives, but not just yet. I mean, obviously they both have this integral symbol, so they're probably related somehow, but right now we don't have a method for, we haven't connected to antiderivatives for evaluating definite integrals, okay? So if we're evaluating a definite integral, like this one asks us to do, we're either going to be using the definition, which is what we're going to do on this one, or we're going to be using some properties, like if it tells us, you know, if it tells us that this is equal to 8 and this is equal to 3, and we want to find this, well, we're just going to do 8 minus 3 and get a 5 there, something like that, okay? Or we're going to use geometry, which I'll do in the last example. Okay, so to evaluate using the definition, which is the infinite Riemann sum, I need to use the same thing that I did in 4.1, okay? So the process is the same. We start by identifying what is delta x, okay, b minus a, 2 minus 0 over n, so 2 over n. And then what is x sub I, which is a plus I times delta x, okay, which is just 2i over n. And then we're going to plug this into the large limit that has a lot of writing in it, but we're going to keep everything straight. Okay, so this integral, 0 to 2 of x squared plus 1 dx is equal to the limit as n approaches infinity of the sum from 1 to n of f of x sub I, which is 2i over n, times delta x, which is 2 over n. Okay? All right, so using correct notation, all of this stays the same, and then I'm going to evaluate f of 2i over n. So I'm plugging 2i over n into f of x, which is x squared plus 1. So I get the quantity 4i squared over n squared plus 1. And I still have a 2 over n behind that, so I'm going to distribute, again, using complete notation. And if you need to pause this and try it on your own, and then come back and see if we have the same thing, that's fine. Okay, so limit at infinity, sum from 1 to n. So I'm going to distribute the 2 over n now, and I get 8i squared over n cubed plus 2 over n, okay, equals the limit at infinity. So now I'm going to use the properties of linearity for summations that tell me I can split this into 2 different sigmas because I've got a plus sign, and then also I can factor anything that is not an I, because I is the variable in the index for the summation. Anything that is not an I can factor to the front. So that's going to be 8 over n cubed times the sum from 1 to n of, and then I have an I squared left over right there. All right, plus, and then here all of it gets factored, 2 over n, and I have the sum from 1 to n of 1 left over. Okay. From here, I'm using the quadratic series and the constant series. These are special sum formulas that were in the 4.1 review that we did at the beginning of the unit. Okay, so we get still correct notation, limit at infinity of, so 8 over n cubed times, and then the quadratic series, n times n plus 1 times 2n plus 1, all over 6, plus the constant series, 2 over n times the sum from 1 to n of 1 is n. Okay, now we're doing some algebra to reduce. Whenever I do the quadratic series with the n plus 1 and the 2n plus 1, I'm actually going to go ahead and multiply those together to be 2n squared plus 3n plus 1. This n I don't distribute because the first thing I'll do is reduce it with the n cubed and make this an n squared. Okay, but I do multiply these two together, I'm also going to reduce the 8 and the 6 to be a 4 and a 3. So now I'm distributing 4 over n squared to the 2n squared plus 3n plus 1 all over 3. Okay? And if you want to write that out in a couple steps, you are welcome to do so. So I have 4 over n squared times 2n squared over 3. The n squareds cancel, and I get 8 over 3. Okay? 4 times 2, n squareds cancel, and I still have a 3 in the denominator. Plus 4 over n squared times 3n over 3. 3n over 3 just reduces to 1. So 4 over n squared times n is 4 over n. And then 4 over n squared times 1/3 is 4 over 3n squared. Plus, and then right here, cancel those n's, we get a 2. Okay? If I have any n's that are left in the numerator and can't reduce with the denominator, then back up because I did something wrong. Okay? Because I shouldn't have an n in my numerator. The only n's at infinity should be in the denominator so that the fractions go to 0. So this becomes 8/3 plus 0, which is what I want out of those, plus 2. 8/3 plus 6/3 is 14/3. Okay? All right. And then the other one here, if you have a question that says evaluate using geometry, that means you need to be looking at the graph in order to see the geometric shapes. And as far as geometry formulas go, we need to know area of a rectangle, area of a triangle, area of a trapezoid, and area of a circle, or part of a circle, like semicircle or quarter circle. Okay? So with this one, because it tells me to evaluate using geometry, I need to look and see what shapes are being formed with this graph. It's a piecewise function. My domain is from 0 to 4. Okay? The function is y equals 2x plus 1 for the first part, from 0 to 2. So we'll call that 1, and then something like that. All right, so this has a height of 2 times 2 plus 1, so a height of 5. And then from 2 to 4, I have y equals 5, which is just a horizontal line. Okay, closed at 4. So when I'm evaluating the integral from 0 to 4 using geometry, I'm looking at this region, this enclosed region from 0 to 4, and I'm going to divide this into 2 different shapes. And I strongly recommend that you divide vertically if you need to cut it into different, more than one region. Divide vertically, not horizontally. Okay? All right, so on the left, I see that I have a trapezoid here. On the right, I see a rectangle. So when I evaluate this integral from 0 to 4, f of x dx, I'm going to do the area of the trapezoid plus the area of the rectangle. Okay? Formula for area of a trapezoid is the average of the bases, and bases are parallel to each other. It doesn't mean top and bottom. So this base right here has a length of 1. This base right here has a length of 5. So average of those times, and then the height is the distance between the bases, which in this case is horizontal, and that's 2. So average of the bases times 2 is the formula for area of a trapezoid. Okay, actually I'm going to reduce those 2's. Plus the area of a rectangle, this is 2, the vertical side is 5, the height is 5, so 2 times 5. So we get 6 plus 10, which is 16.